Right, well done. Just one side problem, they want it in millimeters per second, right? Millimeters per second, right? That's the problem. Well done. Finish. One second. Real? Right? All right, let's see what's up. All right, I'll wait another. Please remember it's millimeters per second, the answer has to be enough. They gave us current, they gave us radius, and they gave us n. So we know I is equal to n in AP. So P is equal to I over n AP. I is what again? 6. N is 1.5 by 10 to the 28. Did we find area? Area is pi by 6.9 by 10 to the minus 4 squared. Push up. I mean, you're all saying it's very good. Right? And here is 1.6 by 10 to the minus 9. Right? What's the value in meters per second? The last one is 1.6 to the minus 90. Just please tell me. Sorry. How much you all got? To the minus what? 9. No, in terms of meters. Oh, yes, 6. I got minus 4 in meters. That's not. Anybody? Anybody can anything online there? What's the value in meters? 6.9 by 10 to the minus 4 squared, right? That's the radius. Remember the radius squared by pi by charge of an electron. I'm gonna put it in correct. I think that's right. Anybody else get that in meters?
Yes.
Yeah, in meters, right? How do I go to millimeters now? That's the amount of meters in 1 second. Divided by 10 to the minus. Huh? Right. So divided by 1,000. How much you got? 0.38. Right? That's the amount of millimeters in a second, right? So just a straight plug in, but You have to pay attention to the unit that they give you. I think so. I have 6 over 3.9 by 10 to the minus 4 squared by pi. That's the area, right?
Well, I'm minus 4.
Yeah, minus. Anybody else get that one line? 0.38. So we should got that. Anybody else got that one line? Look at that. 0.38. Yeah, Arian say you gotta find out. Which one? It's squaring fine too. I have a bracket there. I have a bracket there. Oh, yes, that's correct. If we divide by 1,000, right? If we divide by 1,000, that row, multiply by 1,000, times 0. Huh? I know I said I was wrong. But still bad, right? Still bad. Multiply by 1,000. Yeah. All right, nice. Any questions online? Okay, click also. Got one more trip for us. Quick there. Yeah, but the numbers about 1,000. For the same. No, but and that comes with meters to millimeters.
Yeah.
Why do it now? So if you have 10 meters, how much millimeters is that? 10,000, right? Right?
Yes.
Yeah. Okay, multiply by 1,000. No, we have a second. Right? So that's 1 meter, 1,000 millimeters. Right? So multiply by 1,000, right? The question not done. Nalia, help me out here. Nalia, suggest a reason why this value is so small compared with the other values of electron velocity encountered in physics. Because this value was 3.86 by 10 to the minus 4. That was small. Anybody? Now, why do you think this value is so small? Think about it. I'm just trying to get one more here, right? Think about what it represents, right? Anybody online? Oh, it's a funny. 2022. What do we look like? Yeah. Anybody? One of the main reasons why it's so small is what? Okay, so one of the reasons is because it has a small driving force, but that's not one like, right? The reason why this value is so small is that remember these electrons are constantly what? And they always what? Right? These these electrons are colliding with each other, so losing energy, right? So the energies are not as high as the energies of the electrons. Okay. So write that please. Right, these bars are small because of the frequent collisions. Because of the frequent collisions within the conductor. One and the small driving force that pushes them. I just have one more page, right? But this is 2022. Oh yeah, yeah. Oh, the calculator is 22. Right. I'm FC plus 21. I know. It's I know. All right, just give me 1 second. There's one more question. What is it? This one is 2016. The next one is what is this? Yeah, this is 26. Thanks. Other one out. The one in our module 2, I will give you yet. So you have to remember. You remember each theory and it? What's up? The one I just gave you was 2016. All right. Let's move away from this. All right, try this last one. And this is 2022, but I will give it current value. I'll help you out, right? Right? Because I'm not sure if you remember in theory. Guidance please. I is equal to 0.5 ampere. Come on, hurry up now. Last one. Finish. Return. Ready? I see you doing last week. Where? So why do you look at that? You're lying. You are just a lie. So instead of the way it's happening, yes. When you said you run the 20 minutes. Are you ready? Okay, are you done?
What is the answer?
Who is this is line? I didn't do it now.
What was it?
Right, so obviously you know the formula, right? But you're struggling with the values with each unit, something. Right, so if current was 0.5, there's a module question, yeah? So follow the triple of for module 1 became module 2. And it's 3 by 10 to the 17. Here's 1.6 by 10 to the minus 19. And your area will be pi by diameter divided by 2, right?
Yes, yes.
That was the diameter over 2. What's that? 0.829 meters per second. Yeah? Yeah? I didn't work it out, I'm hoping that correct then. Here, Nigara. Any more answers? Right again, I didn't work this one out. Continue. Oh, right. You'll recognize that the density is in centimeter cube, right? So we need it in meters. Or we can leave the millimeters and centimeters, right? Yeah. Wait, that's not. Right? This is 3 by 10 to the 17 centimeter cube, right? So it might be hard to convert that to meter cube. So we can just convert 4 millimeters, radius is 2 millimeters. 2 millimeters is 0.2 centimeters, right? Yeah? And 2 millimeters divided by 10. Right? So that will be 0.2 by 10 to the minus 2, right? Okay, in centimeters. I'll even the answer in centimeters, right? 0.2. Right? The reason I'm doing that is because the number density is in centimeter cube. So you have to know this. So I'll even everything in centimeters. Right? In centimeter cube, I got, sorry, in centimeters per second, I got 82.9 in centimeters per second, right? And if you want to convert to meters per second, just multiply it by what to do? What to do? Divide or multiply, make a polynomial line. I want to convert centimeters to meters. So divide by 100. 8.29 by 10 to the minus. How much? What's your point? Alright. 0.8, you want me to put that up? Alright, 0.8, alright. Okay, so the problem with this question is not necessarily, but you'll understand n now, right? The problem is working with those exponents, right? Take your time when you're working with those exponents and pay attention to your units. Alright? Alright, let's go again. Let's go back to the notes, right? Alright, last thing. Last thing I want to do today after this. Right? Last thing I just want to do before we start future so next week. You all remember this circuit? If you want to get IV graphs, right, Sean? You remember this circuit here? Right? This circuit here allows us to get the IV characteristics of any components. All right. What does the IV graph for a metallic conductor look like? A nice straight line, right? And the creator of that graph is generally what? R. Well, according to what you've got, if it's IV is 1 on R. If it's V versus I is R. Okay, nice. So that's the graph there, right? That's the graph of our ohmic conductor. Right? If you plot current versus voltage, you will get the gradient as 1 on R, right? It's a straight line, 1 on R refers to Ohm's law, gradient constant. Filament lamp looks like this, right? Why does this part of the graph happen again? In a filament lamp. Because as the filament gets hotter, the ratio what? The ohmic properties begin to die off, right? And during that phase there, it's technically kind of ohmic, right? But as it gets hotter, right, the ratio doesn't behave in a linear. The resistance doesn't behave in a linear way again, and the graph begins to curve, right? Current flow becomes a little bit smaller as it becomes hotter, right? Because the resistance increases. Okay, so that's why the graph is not linear. So as the PD increases, current increases, but it's not a push-up. What would that be? What would that be there? A proportional relationship, right? It is not a proportional relationship. As the PD increases, current increases, but resistance decreases and the gradient, sorry. Right? And the gradient decreases. Right? Here's the graph of a diode. You remember diode? A diode conducts current in one direction only, right? That's why it will conduct here, not conduct here. That's okay? That's the graph for a diode. And lastly, the graph of a thermistor. A thermistor is looks like this. Right? That's the symbol. A thermistor is simply a temperature resistant. Hold on. Right, so a temperature dependent resistance, right? It's a temperature dependent resistance, right? But this is called a negative coefficient. The reason why, as temperature increases, the resistance drops. Okay, this is called a negative coefficient thermistor. All right. So if you see the symbol here, that's a thermistor, which simply means based on temperature, the resistance would change. Right? As the graph showing us, higher the temperature, lower the resistance. That's okay. So we have to be able to draw those graphs, sketch the graph, and explain what you're seeing, right? Again, Make a note of it, this is the temperature, negative coefficient resistor, right? Just make a note of that, please. Yeah. One of the boards is down. Open it. I'll call it quickly. Alright, so that is called a negative coefficient thermistor. Thermistor is simply a temperature dependent resistor. Alright, so the next thing for us to do, and I'm not going to rush that today. The next thing for us to do is something called Kirchhoff's law. Alright, so we're going to focus on Kirchhoff's first, second law and do a lot of calculation. So your homework for the non-math people, the Leon, I'm not saying this, I'm just saying general, the Leon, right? Please learn to solve simultaneously. Please go over how to solve simultaneously. Alright? Go back over how to solve no, you can't use calculator, you will set 8% after you do. Alright? So next week we are going to focus on future first and second law, right? Yeah.